5, last section in chapter 9 that we're going to take a look at. And for some of you who've done contemporary math before, this may have been a section that you've seen some of before, or at least recently. And if you haven't, it may have been a while, or it may be something that you're not quite as familiar with as the others. So we're going to talk about permutations and combinations. And before we do that, we need to talk about a notation. Okay? The notation looks like an exclamation point. It actually has a different mathematical meaning than I'm excited. Okay, it really does. And what it means is this. If we have it's called a factorial. If we have an n and then that exclamation point, that n factorial, it means we take the number n, whatever that number was, and we multiply it by one number less than that, and another number less than that one, and another number less than that one, and we keep doing this multiplication until we get down to the number 1. That's what that notation means. Okay? It's a shorthand way of writing a multiplication that starts at a number and decreases all the way down. Now notice, it only makes sense to talk about this as it's defined right up here if the number is a natural number, because otherwise I wouldn't get to the 3, 2, 1 at the end. Right? So not talking fractions, no decimals, anything like that. There's also no negatives, no negative numbers here in this notation. Okay? So these are natural numbers. However, we do need, for the sake of convention, and you'll see why when we get to an example, to define what 0 factorial would have to mean if and when it does show up. So, by definition, 0 factorial is the number 1. And again, you'll see why when we actually get to discussing this in context of the problems. When you see 0 factorial, it is not 0. It is the number 1. Alright, so we're just going to do a real quick, simple one. What in the world would 4 factorial mean, written out first?
4 minus 1.
Well, we start with 4. Yes. All the way straight down. Okay, so we're going to take 4 times 3 times 2 times 1, and we stop with 1. And what do we get when we multiply those? What is it? 24. So 4 factorial is the number 24. Okay. That's good? Okay, we're going to do a throwback. It's Throwback Thursday, right? So we're going to do a throwback. Throwback to Math 1 for those of you who had it. I know a little bit. I just know Facebook and pictures, that's all I know. All right, so fundamental principle of counting. This was in chapter 2 of this textbook. So it said the following: if you have an event capital M and there are little m numbers of ways that can happen, or you have an event capital N with a little number of n ways that it can happen, and you want to follow event M by event N, then you simply multiply the ways that can happen. And there's lots, it just sounds so weird to even say it because even the N and the N sound the same to me when I say them. So here's an example, Pizza Planet, which is out of Toy Story. My son desperately wants to go to Pizza Planet. What's that?
That Pizza Planet truck is in all of those movies. It's in all of them. It's Pixar movies.
In all the Pixar movies. My son really wants to go to Pizza Planet. Pizza Planet. So, I'm sorry, we're totally off topic now. Pizza Planet offers 3 kinds of salad, 15 kinds, not kids. Does your book say kids? We'll make it kinds of pizza. 15 kinds of pizza and 4 desserts. This is like Mazio's. How many different meals consist of 1 salad, 1 pizza, and 1 dessert? Okay, so this is actually a case that's a little bit more complicated than the fundamental principle of counting directly says. There's 3 events. I'm going to choose 1 pizza, I'm going to choose 1 salad, and I'm going to choose 1 dessert. I'm going to choose 1 of each. So how many different ways how many different options do I have when I pick my salad? 3. How many different options do I have when I pick my pizza?
15.
And my dessert? 4. So the fundamental principle of counting says when I pick things independently, and I can choose them, I simply would multiply those results together. And again, this is essentially what we were doing with all of our tree diagrams along our branches too, where we were multiplying the probabilities together. This is multiplying the number of ways together. So if you multiply 3 times 15 times 4, what do you get? I have 180 written down too. Brendan likes to do math in his head. Okay. It's okay. All right, so there's 180 different meal deals you can get at Pizza Planet under these conditions. Okay? We need that information as we're working our way through these problems. That's another piece here from back when we're going to need. All right, so the first thing we're going to talk about is permutations. All right, so there's two types of permutations. The first set of permutations is a permutation of unlike objects. Okay, so you have n elements and you choose r of them. Okay, so let me start with giving you a formula, and then we're going to do a problem with that formula to show how it works. All right, so the notation is it looks kind of like the n is a subscript in front of the n, in front of the p, and the r is a subscript after it. It doesn't really supposed to look like they're all on the same line. They look like subscripts. And the way that this works is that you have an n factorial on top, and you do n minus r factorial on bottom. Okay? So n in this case might be people, all right? They're n different people. They're all distinct, all right? And you're choosing r of them. The important thing to notice, and that's why it's in red and capitals, and if I could bold it and blow it up huge, that's probably what I should have done. Order matters. If you're dealing with something that's a permutation, it's because the order of something matters. So let's take a look. It says 50 people show up for a game show. 2 of the people will be selected at random to participate. How many different ways can this happen if the order matters? So it actually says it in this problem, order matters. Sometimes you have to make the decision yourself. But in this one, there's a clue. The fact that it says order matters means that you have a permutation. Okay? The fact that there are 50 distinct people, okay, we're not talking about the clones here, 50 distinct people means that we have unlike objects. So what we have for n is we have the number of items we're choosing from. So how many objects are we choosing from? 50. It's a permutation of unlike objects, so the order matters. And how many of them are we choosing? 2. So this is 50p2. That's what it is. And we're going to use the formula to actually simplify what that means in terms of the numbers that we're talking about here. So the 50 at the front is n, so it's 50 on top, factorial. On the bottom, I'll write it out this time. I have 50 minus 2 factorial. So what is 50 minus 2? 48. Now, some of you have fancy calculators that have that exclamation point in them. They have factorials in them. Here's a limitation in your calculator, however. If you try to put in 50 in that factorial notation, it's going to turn it into scientific notation and you're not going to get the full value. You're going to get an approximation. Well, that's not as helpful as it could be. I'd like for us to be able to find it exactly, and we can, but we're going to work with it a little bit more hands-on. So what do I mean? Well, you know what it means to do factorials. I know you know because I just told you. So what does 50 factorial mean? Okay, so Brendan's going to say it a little bit louder.
50 times 49 times 48, etc.
Down to 1, right? So everybody's good with that definition, right? And then 48 on bottom has the same kind of thing going on. Agree? So I'm going to write a few of these out and see what happens. Okay, so there's the top. On the bottom, I don't start with 50, I start with 48, and then okay, so this is all multiplication, right? It's all multiplication on top, it's all multiplication on bottom. And we've done fractions in this class. We've talked about fractions at length. So what are you able to do with this problem? You're able to reduce the common terms. So from 48 down, the top and the bottom match, which means that number that your calculator couldn't handle is unnecessary, because really all the value is 50 times 49. Pretty cool, huh? So let me show you a shorthand way of writing this piece right here. You can do it like this if it helps you to see this, that's fine. But you could also do this. You could also write 50 times 49 times 48 factorial. Because once you get to 48 factorial, they match. You can only cancel out factorials if they're identical. A can't just reduce them. Oh, look, they have a 2 in common. I can't do that. But I can cancel them out if they're identical. And that leaves the 50 and the 49. So what is 50 times 49?
2,450.
Yes.
All right. 2,450. So there are 2,450 ways for this competition, selecting people for this game show, to happen if the order matters. And maybe the order matters because somebody gets to go first, or because somebody gets an unfair advantage over the other person, or something like that. Okay, we're going to change the problem though in a moment. Now, this is not this one, it's one after this one. All right, so this next one is permutation of like objects. So there's an example given here with, and I use this one simply because your book does this. But here's what I want you to sort of imagine. This is the case that I always talk about. Imagine you have a bag of M&Ms. I'm not trying to make you hungry, but within the bag of M&Ms, not every color in M&M is different from every other color, are they? There are some repeats. Okay? And if you want to be more general, or more detailed, you can think about Skittles, because in the M&Ms they all taste the same, but in the Skittles they taste different. Okay? So in the Skittles, we'll use Skittles because of that. In the Skittles, there's like 6 or 5 different colors. I don't know. There's a few different colors, right? It really doesn't matter if you pull out a yellow that was the yellow at the top of the bag or a yellow at the bottom of the bag. They taste the same. The objects are alike. So on this one, we have R1, R2, R3, R4. We've got things that look alike. These aren't people. This can't happen with people. The people are distinct objects. But this could happen with my M&Ms or my Skittles, or my Starburst. I like food. Food works really well to describe this, okay? So when we do permutation of like objects, things work differently. Instead, we still have n factorial on top. But what happens on bottom is that we have R1 factorial, R2 factorial, until we run out of the different looking objects on bottom. So if I had 5 different colors of Skittles, I would have 5 different factorials on bottom, and the number of each of those different colors of Skittles would be those numbers. Okay? So if I had a bag of 20 Skittles, I'd have 20 factorial on top, and if there were 3 yellow, I'd have 3 factorial on bottom, and there were 5 red, I'd have 5 factorial on bottom, and so forth until I ran out of my colors, and total up the total of the 20 Skittles I have.
So the top is the total.
Exactly. The top is the total number of everything in the bag of Skittles. The bottom is the total number of the individual components that are alike. So we're going to do it with an example that's not food. We're going to do an example that's Tallahassee. So the word Tallahassee has a lot of letters, but a lot of them repeat each other, don't they? So if you were to use the word and simply rearrange all the letters and want to find out how many ways that can happen, then we could actually do that, but it really doesn't matter whether you use the first L or the second L, you use an L in a certain spot. Okay? So first thing we're going to do is we're going to write out each of the letters, just make sure everybody counts in the same way. H, S, and E. Did I get all the letters that are different? Okay, how many T's are there? How many A's? 3. How many L's? H, S, and E. Okay, so how many total letters are there? 11. Okay, everybody good? So you're counting, just like with the Skittles. So what's going to go on top? What's going to go on bottom? Yeah, Brendan's right. It's going to be factorials of all those individual letters.
Order doesn't matter,
The order still matters. That's why it's a permutation.
but you don't have to.
But
put
the
it
order
in
of the
consecutive
individual
order.
letters is indistinguishable. There's no way for me to tell if the L in the third location was the first L or the second L. Those are indistinguishable permutations that I can't tell them apart.
But you don't have to put it in numerical order.
Oh, on bottom? No, it's making the calculation the same.
So what
So for instance, if you had let me do as though it just were the letter tall, just because I don't want to write them all out. So let's say the head letter tall and I were doing, word tall and I were doing this. Well, the word A-L-T-L would be the same as the word A-L-T-L, but I shouldn't count it twice. Right? Because all it did was switch the two L's. Well, that's indistinguishable. I can't tell the difference when I look at it. So I shouldn't count it twice. So when I'm dividing by these right here, that's removing those double counts. That's what it's doing. Something else that's different about this one than the last one is, notice in the last one we had 50 people we were choosing from, and how many did we choose? 2. Here I have 11 letters I'm choosing from, and how many am I choosing? 11. I'm choosing them all. That's different. Okay? All right, let's figure this out. So one of the ways that I could simplify this, this isn't grand because I don't have a lot of numbers down the bottom. They're big. They're all pretty small. But I could write down 11, 10, 9, 8, 7, 6, 5, 4, and I could stop at 3 factorial at least. What is 1 factorial? 1. So these 1s don't really affect anything, right? There is a 3 factorial here. And then what about these 2 factorials? What do they equal? They're each 2. So in looking at how this can reduce, the 3 factorials can reduce. And then what's 2 times 2 times 2? 8. So in your numerator, which is all you've got left, you have 11 times 10 times 9 times 7 times 6 times 5 times 4. And what do you end up with? How many did you get? Okay, is that what you got, Brenna? Okay, then I've got an arrow. That's fine. 831, what was next? 600? All right, so just like that.
If we don't recognize the 2s, are we going to get it wrong?
Well, you have to reduce it somehow anyway.
So, I mean, but if you did the reducing that we went on the first one, where we just cross out the bottom.
Okay, but what do you want to cross out on the bottom on this one?
The 3, 2, and 1.
We did that. That's this 3 factorial that reduced
What
here.
if you don't recognize the 2, so you don't cross out the 8?
Well, these 2's are still here because they're here, here, and here. They got to be somewhere. So let me answer the question maybe a little bit differently, Devin. What you could recognize if you didn't say, oh look, there's 2 times 2 times 2 and it's 8 and I have an 8 on top, is you could multiply the whole numerator out with that 8 in there, and you can have the denominator be an 8, but then you're going to have to divide when you're done. Because you wouldn't leave the 8 on bottom when you reduce with what's on top. In the end, the answer will be the same. Yes, indeed.
I think screws like if you wrote like a 2 and a 1 on the top still, and then mark one of the 2's out, one of the 3's out.
Well, but it wouldn't mark out a 3 because this is 3, 2, 1, and there's a 3, 2, 1. I mean, no matter which way you do it, only one of those 2's is going to be marked out. So if you want to write all of them out, it's fine. The reducing is still only going to reduce with one of the 2's. There's still going to be 3 2's in the denominator left. Okay, we can do that. All right, there is a situation where the order does not matter. Big, bold, red, everywhere. Okay, it's called combination, which is unfortunate, and your homework will show you why it's unfortunate later. But it's unfortunate to call it that. So, combination, the order doesn't matter. Let me show you the formula for it, and then we'll do an example of a problem with it. So the formula for doing this, it is NCR. So it's a combination, N items. So there's still N things you're choosing from, and you're still choosing however many of them you're choosing are. The formula looks like this. You've still got the N factorial on top. You've still got an N minus R factorial on bottom. But you have an additional R factorial on bottom as well. So there's an additional piece on bottom. So in general, will this number be bigger or smaller than you get when you did permutations? Smaller. Why? You're dividing by more. There's extra stuff you're dividing by. So you divide by more stuff, right? Numbers that are bigger than 1, the number gets smaller. So this is a smaller number than when you do permutations. And the reason is because order doesn't matter. If the order doesn't matter, it doesn't matter if you're picked first to be on the baseball team, or third to be the baseball team, or last to be on the baseball team. You've got to be on the baseball team. Same team players. All right, so here's our 50 people that showed up for the game show now. But in this case, the order does not matter. Okay, they both get on the game show, they both get to play each other. It doesn't matter whether they were picked first or they were picked second. They still get to play. So it's a combination, right, of 50 objects, in this case people. Whoops. And we're choosing 2 of them. So what's going to go on top? 50 factorial. What's going to go on bottom? Okay, so I'm going to write it out in one step. You don't have to, but just to make sure everybody sees. There's the 50 and the 2 here, from here. And then there's an extra 2 factorial on bottom that was not in the slide 2 slides ago. It wasn't there. All right, so this is again like what we did before, where we can recognize that this is 48. Then we can recognize that we can write this as 50 times 49 times 48 factorial, because at that point it identically matches one of the factorials on bottom. And then I've got the 2 here, so this is 2 or 2 times 1. So the 48s cancel. What else reduces? Well, the 1 does. What else? You can do the 50 and the 2, yeah. So the 2 and the 50 and the 50 would become a 25. If you don't reduce that there, it's okay. You're just going to have to reduce it at the end. So this really boils down to 25 times 49, which is what value? Half as many ways, if the order doesn't matter, to select those 2 units. Okay? All right. All right, we're going to do this one slide, and then we'll finish up the last 3 slides next time. Sure. All right. All of this chapter is about counting methods, ways that we can count things and we can find probabilities. This problem looks a little bit different. This one says if all telephone numbers or all phone numbers on campus are 405-858 and then a 4-digit number at the end, how many different telephone numbers are possible? All right, so this isn't a permutation, this isn't a combination. Okay, it isn't. What would we do in order to find out the number of telephone numbers that are possible? Right. So this is one of those fundamental principles of counting, like Pizza Planet. Right? I have 4 different numbers. How many different options do I have in each of those locations? 10, because I'm going to use number 0 as well. So 0 through 9, I have 10 different units. And what is 10 times itself 4 times? That is 10,000. So there are 10,000 campus phone numbers if they start out with those same first 6 digits in essence. And they just have 4 different digits at the end. Here's another one. There's at least a couple ways to do this problem, so we'll see what you guys come up with. A worship team practices 8 songs on Wednesday night for the Sunday service. If the minister plans to choose only 5 of the 8 songs practiced, in how many ways could the songs occur? What kind of things are you thinking? Okay, so that's one way of doing it. Did anybody else see anything different?
10
show you two different schools of thought for this one. One is to think about it as a fundamental theorem of counting, so that it looks a lot like example 6. I'm going to select 5 songs, like so, and I have how many songs to choose in the first song? I have 8 of them. How many for the second song? Now, you're able to do this only because of one phrase in the problem. So let me know what that phrase is. Well, that's part of it. Not what I was thinking of, although that does affect things. If you were to select, have the ability to select more, that would change the problem. Yeah. In how many ways? So what is in how many ways telling you? Is this a combination or a permutation? This is a permutation because the order matters. My husband's a worship minister. Does the order matter in the songs he picks? Yeah. He was very frustrated with himself on this past Sunday, in fact, because he had something in order that he didn't intend, and it got all flustered and things didn't work out right, and nobody in the congregation had a clue. But it mattered to him because it didn't flow the way he anticipated. Okay, so it mattered, okay? The order matters, and it matters in part simply because of what we know about the songs, but also because it said in how many ways, right? That is, if I switch the first song with the third song, that would be a different way of doing those 5 songs. So if I were to do this with permutations, I would have 8 songs, and I would be picking 5 with a permutation. Because it's a permutation, it's actually using this fundamental principle of counting. If this problem, instead of saying in how many ways, it simply said how many different song collections could he have picked, it wouldn't be a permutation. It'd be a combination, and I would not be able to do it with 8 times 7 is 654. It wouldn't be possible to do it that way. Okay? So let me show you what happens. I know you can multiply this one out. Let me show you what happens with permutations, because we haven't done very many of them written out. What goes on top on a permutation? The 8 factorial. What goes on bottom? 8 minus 5 factorial, which gives me a grand total of what? It's actually 3 factorial. So we can either multiply that out as it is, or we can write it. I'm going to write it just because I want you to get in the habit of seeing that. 8, 7, 6, 5, 4, and why do I know I can stop at 3? Because it identically matches what's on bottom. Oh my goodness. What happened? Alright. Happens to me. Alright, so the 3's cancel. And do you see 8, 7, 6, 5, 4? There it is. Is that 8, 7, 6, 5, 4? What is 8 times 7 times 6 times 5 times 6? So there's 6,720 different ways that 5 of the 8 of the songs could have been performed. Wow. Yeah. Okay, so we totally don't have time to do much group work, but let's do this. Does everybody know who their group work partner is? Excellent. Move and get in groups really quick. I'd like for you to do one problem before you go from 9.4. 9.5 is not assigned, although I would encourage you to start taking a look at it over the weekend, so that you can finish it quickly on Monday, Tuesday. Yes, ma'am.